Welcome everybody in the lecture hall. Welcome everybody on Zoom. Today we are going to continue on this part that we started last week, which is about views and indices. And I'm going to start with a few questions, actually looking back to what we've been doing before. So here's the first one. These are 4 statements, and I would like you to mark those that are correct. The first statement says that a functional dependency holds for an entire table universe, right? You remember a table universe is all the possible tables at points in time that could be in a specific schema in PostgreSQL. So a functional dependency holds for a table universe when it holds for all tables in the table universe. Then the same thing for the super key. Does it hold for a table universe when it holds for all tables in the table universe? Then candidate key. Does the candidate key hold for a table universe when it holds for all tables in the table universe? And then unique constraint. Does it hold for a table universe when it holds for all tables in the table universe? So again, the idea is that when you create a table in PostgreSQL or in a relational database, it has a life. Right? There's not just a single table forever. It evolves. And so the table universe is all the potentially allowable tables that could hold the actual data. So when you design a schema for a company or a web shop and you think about functional dependencies and normal form, you might look at a sample, but you always have in mind that you're reasoning actually on things that should be for the universe. Okay, so we have a few responses that came in. So let's first see what you said. There is a disagreement. So the super key, you all agree. The unique constraint, you don't like that one. Okay. So let me show you the answer. I think I need to click somewhere. How do I reveal the correct answer? I think I also need to click. I'm still learning with show correct answer. Yeah, there you go. Exactly. So all 3 of them except the candidate key. So when you have unique constraints, you remember it's not null, unique, check, all these things we can have in SQL. These are forever. They hold for the entire universe if and only if they hold for every table in the universe, right? That's the goal of these unique constraints, okay? The super key is the same. We say we have functional dependency. Maybe I should start with functional dependency because super keys are defined on functional dependencies. So we say that a functional dependency holds on the entire table universe, meaning forever on all states of the table. If it holds for every single table in that table universe, that's the definition we gave for a functional dependency on a table universe, right? That it holds for the universe if it holds for everything. And then the super key was also defined like this, that we say since the functional dependencies hold for the entire universe if they hold for every table, and the super key is only defined in terms of functional dependencies, right? It's the idea that you have a set of attributes that determines everything, all the other attributes. So you have a functional dependency where the left-hand side is your super key and the right-hand side is everything. Then it also holds for a table universe if it holds for all tables in the table universe, right? But the third one is the one that is interesting. Why is it not true for a candidate key? How did we define a candidate key? Does anybody remember how we defined the candidate key? It's a minimal super key, exactly. A candidate key is a minimal super key. It means that it's a super key and you can't remove anything. If you remove anything, then it stops being a super key. And so that's also how we define a candidate key on a table universe, right? It's a super key on the table universe where you can't remove anything. And so it's actually not true that a candidate key holds for a table universe when it holds for all tables in the table universe, because we can have accidental superkeys. You remember what I showed you on the slides a few weeks ago? You might have, for example, the inventory, the number of the quantity of everything you have in the inventory. You have 2 TVs, you have 3 phones, you have five tablets. Normally, you agree the inventory is not a superkey, right? That wouldn't make sense for it to be a superkey, because you could have equality, you can have multiple things that are in the same quantities. But just by coincidence, maybe exactly today at 2:34 p.m., there will be unique inventories, just by chance, just like that. And then it's a superkey, because it would determine everything, right? If you have an attribute where everything is unique, it determines everything. But it's an accident, right? It just so happens by coincidence that at that point in time, it's a superkey. So basically, this is something to be careful about, because you might have superkeys for individual tables that just pop out of nowhere by chance, just because of the data that sometimes, it's like you look at the alarm, at your alarm clock, and it says it's 11:11, right? And that's by coincidence, you notice, oh, there's only ones in there, right? It's just a coincidence. And because of this, we might have a candidate key for a table universe where you can't remove anything before stopping to be a super key. But because of these accidents, you might have, in some cases, that you can remove something and it's still a super key. It remains a super key, but it's only by accident. So technically, for that very particular table, the original super key was not a candidate key for that particular table. So this is why you have to be careful with the table universes, right? Do you remember that slide I showed you about the quantities? Right. So this is the one thing to be careful about when you reason about table universes. Super keys, functional dependencies, unique constraints, that's all easy, right? Holds for the universe if it holds for all tables, but be very careful. The candidate key is the one thing why you can't say that. You can't say that because of these accidental super keys just by chance. All right. So this is it for this question. Then here is the next one. I'm not getting my mouse. I'm not sure where my mouse. Oh yeah, there it is. Oh yeah, there you go.
So superkeys can't have accident superkeys, but candidate keys can.
Well, you can have, so basically the superkeys, they can be accidental on individual tables. Then it would not be a superkey for the entire universe, right? Imagine you have 1 million tables, and in let's say 10 cases, there is by chance a superkey, but it's not a superkey for the other almost 1 million tables, right? Only 10 have that superkey. Then that's clearly not a superkey for the entire table universe, right? It's only a superkey for these 10 tables by accident. But then imagine you have something that is a candidate key for the entire table universe, and it's also a candidate key. Sorry, it means that it's a superkey for every table. Candidate key means you can't remove anything before without it stopping being a superkey. And so what happens is that in the case of these 10 tables that might have an additional superkey, for these specific tables, when you want to see, is my candidate key a candidate key for that table, the candidate key of the entire universe, you want to test, is that also a candidate key for these 10 tables? And the answer might be no, because you might remove an attribute from that candidate key of the universe. You remove an attribute, but accidentally for these, even removing the attribute, it's still a superkey, an accidental superkey. And then what would happen is that this candidate key of the universe might not be a candidate key for some of these tables, because for some of them, you can remove attributes and it's still a superkey by accident, right? Does it make more sense?
Yes.
Yeah. I have a slide, if you look it up, or I can show it again maybe later. I have a slide on that, on the accidental superkeys with exactly an example of that. And maybe otherwise I can show it to you. All right. Did it answer the question?
Yes.
Okay, awesome. So that was just a bit of a warning. But at the exam, we don't bother you too much with that because we try to give you tables that don't have accidental super keys because it's too confusing. So we try to really give you tables at the exam that are representative of the universe. We express it like that. The table is a good sample. It's representative of the universe. So you don't have to worry about accidental super keys, right? It gives me headaches every time I think about this. You saw how I was like carefully formulating my sentences. Like you just get headaches with these things. All it means is when you design a schema, try to pick a table that doesn't have accidental super keys to not make mistakes in the design. All right. So now the next question is that there's things that are unique and there's things that are not unique. And I think some of you already asked the question. So if I tell you the closure of an attribute with respect to a set of functional dependencies, remember you can compute the closure of an attribute or even a set of attributes. Is it unique or is it not unique? The closure of a set of functional dependencies, it basically means all the functional dependencies you can derive using the rules, all of them. That would be huge, right? But is it unique or is it not unique, the closure of the set of dependencies? Then we have the minimal basis of a set of functional dependencies. Is it unique or is it not unique? And the super key of a relation, given a set of functional dependencies, is there only one or is it not unique? So you need to pick the ones that are not unique. Everything that's not unique. And the ones that are unique, then you don't pick them. Let's start seeing what you said. That's the second one. If I click here, now we see the answers, okay? And I'm showing the correct answer. These are the two that are not unique. Remember that a super key is just the left-hand side of a functional dependency where there's everything on the right? It's a set of attributes that determines everything. There could be several of these, right? Remember, you could, for example, you might have a table of people, but you can identify them in multiple ways. Maybe you can identify them with a social security number, with a Leggy number at ETH. So imagine a table with a Leggy number and with a social security number of students. Do you agree that both of them would be super keys, right? So super keys are not unique. And then the minimal basis, do you remember, it's when we tidied up these sets of functional dependencies, right? We reorganized everything to try to have less of a mess and all tidy. That was the minimal basis. And I also observed that there's multiple ways you could tidy it up. Depending on in which order you tidy things up, you might end up with a different minimal basis. So a minimal basis is not unique, also not. But a closure, it's always unique, right? Because the closure of an attribute, for example, you're basically saying, okay, if I know the value of that attribute, what do I know? Well, the closure is just all the attributes you then know, right? That's totally unambiguous and that's unique. There's only one closure. Right, so that's it. And the closure of a set of functional dependencies that I did not mention, so don't worry if you never heard of that. It's again, the idea of a closure is that you try to put everything you can. But when you're talking about the closure of a set of functional dependencies, you're just trying to add more and more and more functional dependencies, everything you can add thanks to the rules, right? And that is also unique. Technically, a closure is always unique, right? A closure in a graph is basically all the nodes you can reach from where you are. That's always unique. Who is with me? Right? Okay. But what you should remember here is be careful. You might have multiple super keys, and you might have multiple ways of tidying up a set of functional dependencies, multiple minimal bases. All right. Where is my mouse? It's crazy. I'm using the trackpad, but the mouse is not showing anywhere. I'm not sure what. Oh, here it is. There you go. Okay, and now to evaluate, I would like to understand how confident you feel about a few things, just for me to see. So the first one is, if somebody gives you a table, you can tell whether or not a functional dependency applies to it. Can you do that? If yes, then you can pick that. The second thing is, if somebody gives you a list of functional dependencies, you can tell whether a set of attributes is a super key or not. Right? So you can tell me yes or no, this is a super key. I don't show you the table, just the functional dependencies. Can you tell whether something is a super key or not? Then the next one is, if somebody gives you a list of functional dependencies, then you can tell whether or not something is a candidate key, right? By trying to remove attributes and seeing if it's still a super key or not. So can you tell whether or not something is a candidate key? There's probably a formatting issue here. The fourth one is, can you tell whether or not a table is in the first normal form? Yes or no? And the fifth one is, can you tell whether or not a table is in the Boyce code normal form, if I give you the functional dependencies? I just want to identify and point you to things that you can focus on maybe offline to rehearse for the exam. Right, so these are very concrete things that you can or cannot do. And I want to see what is really mastered and what can cause more issues. So I see the first normal form. This one will be easy to explain, that I'm not worried about. I can explain it in just a few seconds. And the Boyce code normal form, yeah, it's a bit more tricky. Maybe start with the first normal form. Can anybody tell me what the first normal form is? Does anybody remember? Yes? Atomic integrity, exactly. The first normal form is just another name for atomic integrity. All that means is you cannot have anything nested in the table. You can't have tables in tables in tables in tables. So first normal form just means you just have simple values in every cell. That's all, right? So who can tell now, raise your hand, if a table is or not in the first normal form? Right? Just by looking at it, you see immediately if you see, is there anything nested or is it just simple values? So now you can, okay, that was the easy one. And the Boyce code normal form, does anybody, this one is more complex, do you remember the definition of the Boyce code normal form? Yes? Yes, that's exactly it. So I'm repeating for the people on Zoom. In the Boyce code normal form, you have a requirement is that you can only have non-trivial functional dependencies where the left is a super key. Otherwise, you can't. And I'm saying non-trivial because you can always have A determines A, you know, that kind of things. That's always true. And obviously, you don't want to restrict here. But the non-trivial ones, the ones that are actually meaningful, you can't have any one of them where the left is not a super key. That's the Boyce code normal form. So it's more complex because it involves more things. But since a lot of you said that you can tell whether something is a super key or not, then normally you should mechanically be able to determine if something is in the Boyce code normal form, right? So it's easier to show something is not in the Boyce code normal form because then all you need is to show me a set of attributes that's not a super key, but that is on the left of a functional dependency that's not trivial. And that's enough. Just a counterexample is enough. Showing that a table is in the Boyce code normal form, it's a bit more involved because then you need to show that every time you have a non-functional dependent, a non-trivial dependency, the left is a super key. Okay, who is with me on that one? Right. Okay, so maybe this is the one, the last one. You can maybe look at it again offline and see if you can look again at some examples for the Boyce code normal form. What's really nice is that you don't even need to look at the table for that, for the Boyce code normal form. You can just tell with the functional dependencies. Okay, and here's another 4 more just to see if you there you go. So if somebody gives you a set of functional dependencies, can you or can you not compute the closure of a set of attributes? That's the game we played 2 weeks ago. The second one is, If somebody gives you a set of functional dependencies, can you tidy it up, compute its minimal basis? Remember, it's not unique. Maybe several ways to tidy it up, but can you do it? The third one is if I give you a table and a functional dependency whose left-hand side is not a super key, which means that it's not in the which normal form? Boy's code, exactly. So if you have a table that's not in Boy's code normal form, and in order to show that, you found a non-trivial functional dependency where the left-hand side is not a super key, are you able to decompose it, to use these functional dependencies to split it into two tables? That's the algorithm I showed you last week and 2 weeks ago. And the last one, can you use the chase algorithm? Do you remember the chase algorithm? It's the bingo game, right? You want to see when you decompose a table, can you build it back with a join? You decompose, you build it back. Do you get back to where you were? Do you get back the original table? And for this, there is the chase algorithm where you start putting these numbers in the cells like the bingo. And if at some point you have the full line filled, then bingo. And then you've proven that it's lossless. Lossless just means that you can build it back exactly with a join. You're not losing any information. Okay, so what do we have? So you're good at computing closures. That was easy, right? Computing a closure is quite intuitive to do. Tidying up, very nice. A lot of you can do it. Decomposition, then maybe this is something you could look again. Imagine that I have, let's say I have a table A, B, C, D, E. These are my 5 attributes. And my functional dependency that breaks the Boy's code normal form, let's see that it is AD, A and D, determine E, right? That clearly breaches the Boy's code normal form, right? Because AD, if it's the only one, because AD then doesn't determine everything. So if we have AD determines E that breaks the Boy's code normal form, can anybody tell me how you will decompose that table into 2 tables? In the form of 2 sets of attributes, the one of the first table and the one of the second table. Can anybody tell me that? AD determines E. Let's start with the first table. What do you put in the first table? Maybe I can add that AD determines E, so the closure of AD is ADE, right? So what would be the first table? Yes? Yes, that would be one of the tables, absolutely. A, B, C, D. That was the more complex one that you found. So congratulations. What was the other one? The other table, the one that is simpler to find? ADE, yes, exactly. So the one that is easy to find, it's just the closure of the set of attributes that's guilty of not being a super key. You compute its closure, and that gives you the first table. And the other table, do you remember in general how you build the other table? So you said indeed it's ADBC. What's the general way of computing that other table? The second one? So it's basically the set of attributes that's guilty of not being a super key plus all the rest. So in that case, what is the set of attributes that's guilty of not being a super key? It's AD. Right? It's not a super key, and although it's on the left. So AD is basically the thing you want to join on with these 2 tables. So AD, you want it on both sides. AD is on the left, AD is on the right. And then you put the closure on the left, ADE, and on the right, all the rest, AD, and then B and C, which is the rest. Okay, who is with me? Right, so that's how you decompose it, right? Pretty simple. Again, you can train on a few examples to do that. The chase algorithm, then yes, this one is a bit more complex. It's just a bingo game. So here you could take past exams. There's examples of that also in the book. There's a few examples, so try to train you. The setup is really, we give you a table, we give you functional dependencies and the decomposition, and we ask you, okay, use the chase algorithm to determine if the decomposition is lossless, right? Of course, if you pick the decomposition in the way of the point above and you did it correctly, it will always be lossless. And the chase algorithm will always lead to a bingo. But if you try to decompose it in some other way, randomly, then it might not lead to a bingo, and then the chase algorithm might fail. Okay, so here my recommendation offline, the last 2 points, I recommend you take a look again if you're uncertain and train yourself on past exercises and past exam questions. Okay? All right. I had a few more, but I'll come back after the break on these, maybe to not just do only questions right now. So let's I'll talk about serializability again after the break. Now let's continue where we were. Right, I showed you the views, create view. So you can create a view that is that gives a name to a query, so that you can reuse the name instead of rewriting the query every time. Right, we saw that there's views that can be materialized. You can choose to materialize it, or you can choose not to materialize it. Right, if you materialize it, then it means you take a snapshot and make a copy somewhere, and then it's faster because you already have it. But the problem is that if the data keeps changing, you might no longer be up to date with your materialized view. And if you don't materialize the view, then you compute it every time you use it. That's the idea. Who remembers the views? Right, very good. And then I started with indices. For indices, I explained to you the goal is to make queries faster. You have a table with 1 billion records, and you want to very quickly look up one of the records. How do you do this? You use indices. When I say you, it's actually PostgreSDB, because, PostgreSQL. PostgreSQL is doing that all for you. All you do as a user is you notice it's faster. That's all that happens. And so I left you with this, where I gave you some list that happens to be alphabetical, just for the sake of showing to you how a human would do this. And then as a human, you immediately spot it, because the reason you spot it immediately is that you do a binary search, right, alphabetically, and then you cut it into every time until you find it, right? This is a quite natural thing to do, and that's how you use a dictionary also when you look up a word in a written dictionary. Parenthesis, dictionaries are allowed for the exam. If it's in English and you don't feel sure about your English, you can bring a bilingual dictionary. It's totally fine. Okay, so essentially what happens when we as humans do the binary search in this way is that we in fact implicitly build a tree in our minds, right? We cut it in two, we compare, and then we go on the right or on the left, depending, right? In that case, here, 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 and here we find it. And the reason it's magic is that we did not even look there. So the magic of indices is that we can be much faster because we are no longer looking at the entire table. Without index, we have to scan the entire table to find what we are looking for. But with an index, we can be smarter and use less. And the last thing I told you last week is that the complexity of this is the algorithmic complexity. Logarithmic, exactly. It's logarithmic. Meaning that going from 10 to 100, from 100 to 1,000, from 1,000 to 10,000, it's only adding a constant time. Right? So this is extremely efficient, and in computer science, we absolutely love logarithmic algorithms. In that case, it's the way you see it's algorithmic is that when you have a tree like this, with it's called a binary tree, what you see here, and there is n nodes in n values in that tree, right? In that case, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? You call it n. What's the number of colored cells? Well, it's typically the logarithm of n. In that case, around the logarithm of 11 in base 2, right? And so this is why we say it's logarithmic, just because the height of the tree, the number of nodes on a single path, is roughly the logarithm of the total number of nodes in the tree. Who sees that? Right? Okay. So in fact, what we've done here is we've built an index. And in fact, we can ask PostgreSQL to build indices. So there's two ways that PostgreSQL builds indices. The first one is called the hash index. And the second one is called a B+3 index. Who has ever heard of this? Who has never heard of hash indices? Okay, so I'll start with hash indices. Then I'll give you the B+3 indices. So the hash index works like this. So imagine I take this table, 3 attributes, 6 records, and I would like to index the century column. I would like to very quickly look up the people by century, so I want to index it. So what PostgreSQL is going to do, this is really what PostgreSQL does. If you ask it to build such an index, it's going to go row by row, record by record, and it's going to build the index. So it's starting with the first record. And it's saying, OK, century is 20. So what it does, there's a trick. Actually, it comes from cryptography. Who has ever heard of a hash function? Okay, who has never heard of a hash function? Okay, who has ever done smoothies? A hash function is basically a smoothie machine, right? You basically put whatever you want in there, you press the button, and a number comes out. It's a smoothie machine. But it's a smoothie machine that is deterministic, meaning that if you put the same thing in, you will get the same number out. That smoothie machine is h. That's the function h. We call that a hash function. What is there in that smoothie machine? Well, it's actually surprisingly simple because it's just a bunch of addition, multiplication, and modulo, right? You just hash the whole thing and then get some integer at the end. So it's h. That comes from cryptography because it's very useful for encoding and decoding things securely. All right, so what we do is that we have this smoothie machine, could be any smoothie machine. There's good smoothie machines and bad smoothie machines, of course. We assume it's a good smoothie machine. I will explain what it means to be a good smoothie machine. But let's say the good smoothie machine that we call H says H of 20 is 0. You put 20 in the mixer and you get 0 out, right? So then we put 20 at position 0 in this array on the left. By the way, just in case you're not aware, computer scientists love to count with 0 when they index position. So 0, 1, 2, and so on. So this is why the first position is position 0. So we put 20 at that position 0 that we get out of the mixer. And then we put a pointer from where you are in the second cell to the records. And then we just do the same for every record. We go to the second one. Happens to be 20 again. I put it in the mixer. What do I get out of this? Again, 0, because I told you it's a deterministic smoothie machine, right? Always gets the same thing out. So it gives you again 0. And then what you do is you just add the records. Then you have 19. So let's put 19 in the smoothie machine. What do we get out of the smoothie machine with 19? We get 4. Right? Impossible to predict. That's also why I'm saying it's useful in cryptography. Nobody can tell in advance what's coming out of the machine. It's a bit simplified, but just the idea I want to give here is that if you have a good smoothie machine, it will more or less distribute everything evenly in the array in a way that seems a bit random. That's what I want to say. So we put 19 in the smoothie machine, we get 4. So we put 19 at position 4. And again, since we start counting with 0, that's 0, 1, 2, 3, 4. So you see it's position 4, plus the pointer. Then the next one is Euclid minus 4. So we put minus 4 in the smoothie machine, press the button, what comes out of it? 3. So we put minus 4 at position 3 with a pointer, then minus 6 in the smoothie machine gives us 1. Then we put the arrow, and then 20 in the smoothie machine gives us 0. Okay, who is with me? Right? And so this is exactly what PostgreSQL is going to do. If you ask PostgreSQL to create that index, and what you have on the left, the red table is a hash index. That's exactly what it is. This is the original table, the one that you created and in which you put data. This here is something additional. It takes space, of course, in memory or on the disk. This is a hash index. Now, imagine, so I'm done building that hash index, and somebody arrives and types a query in the system, select star from scientists where century equals 19. Can anybody drive me through what's going to happen with the index? Because now I have the index. How can I use the index to answer that query very quickly? On Zoom also, we can, yeah. Yes? Yes? Yep. Yep, absolutely. So I'm repeating for the people on Zoom. you put 19 in the smoothie machine. I'm not using the same words, but this is what you're saying, right? So we put 19 in the smoothie machine. We call h of 19. We get 4. It's deterministic, right? It's a deterministic smoothie machine. So it's always going to give us 4, just like it gave us 4 when we actually built the index. What do we have at position 4? Oh, it's 19. How nice, right? But of course, we build it in this way. So then we go, as you said, to the pointer and follow it, and we immediately find the 19. Now, can anybody guess what the algorithmic complexity of doing that is? Is it linear? Is it exponential? Is it quadratic? Is it the square root? Is it logarithmic? Is it constant? What do you think is the complexity of that? Yes? Constant complexity. Absolutely. Constant complexity. Let me explain constant complexity because maybe not everybody is familiar with complexity theory. Let me give you the feeling of constant complexity. Here, there are 6 records. We answer in 2 milliseconds, let's say. That's a perfectly normal response time for a query with an index like that. Let's put 100 records in the table. How much time is it going to take? I'm assuming the query is selective, right? So it's not too many to return. How much time is it going to take? Again, 2 milliseconds. Imagine the table now has 1,000 records, still 2 milliseconds. 1,000,000 records, still 2 milliseconds. 1,000,000,000 records, still 2 milliseconds. You can instantly look up the values in your tables as long as it's relatively selected. Because of course, if your query outputs 1,000,000,000 values, then of course, that's not going to take 2 milliseconds to print 2,000,000 values on your screen, right? But looking up is instant, it's magic. Why is that magic? Well, look at what we're doing here. You can see it's immediate because calling h is just a bunch of plus multiplication modulo, simple mathematical operation, and you just do it on the value. So that's independent of the size of the table, right? You just put 19 in there. So who agrees that part is constant time, constant complexity, right? It's immediate, just a bunch of arithmetics. Who agrees that with that value 4, jumping to position 4 in the array is immediate also? That's constant time. Right? Do you know why it's constant time? It's because what do we call the working memory in a machine? What are the 3 letters that identify the working memory? I'm sure you all know it. You saw it on shops. Yes? What is it called? The RAM, right? It's called the RAM. What does RAM mean? Random access memory. It means random access memory. That's exactly this. Random access memory basically says, I know position 4, so I know immediately the address in the memory of that position because it's just sorry, you compute the size and multiply it with the position, so you know exactly how many bits you need to jump to go here. And random access memory says it's instant. Random access, you immediately go there without waiting. That's why it's called RAM, random access memory. So this is also constant. And this here, going to the record, it might be on disk, but you know that even though we don't call them random access disks, you know that you can also go anywhere on your disk. Right? It's not like the tapes. Back then, when you had tapes, you needed to really play the tape all the way to where you want to be. But in the disks and SSD you have in your laptop, that's no longer the case. It's also instant. You go directly where you want. Maybe a bit slower than the memory, but it's still instant. So you see, every step in here is instant. Even if I have 1 billion entries in my table, that is still going to be instant. Who sees that now? Right? That's the magic of hash indices. It is instant. Right? That's beautiful. But of course, you know that everything in life has a cost. And so since you get something that beautiful as instant lookup with 1 billion entries in 2 milliseconds, you locate them, there is a price to pay. Can anybody tell me what the price is? There's two costs, actually, 2 prices to pay. What do we give up for that? What do we have to pay? Yes? Absolutely, that is the first cost. It needs extra computation cost to create the index. All of that, we do it once, but it does take a bit of CPU power to do this. And when you do that, it's slowing down the database. When you tell PostgreSDB, please build an index, then for a while it builds the index, the entire database system is going to be a bit slower because some of the resources of the machine are used in order to build the index. So this is the first cost to pay to build the index. A part of that cost is also, it's directly related to what you said. If I update the table and I add a record or I modify a record, do you agree we need to also update the index? Right? So it means that whenever you update the table, the update is going to be a little bit slower. It's going to be a little bit slower because you don't just update the table, you also update the index, right? So it's a related cost, so more computation. Another cost? The space, absolutely. That is the second cost. The space that you need for the index, this table here, the red table, it takes space in memory or on the disk. So that is also a cost. You need a larger hard drive or you need more memory. And if you want more indices, then you need even more space and more memory. Who is with me? Right? So we pay it in the sense of resources, that it costs time to build the index, and we pay it in terms of space, that we need more memory or more disk in order to fit the index in there. So it's not free. We get something beautiful, the instant lookup of the values, but the price to pay is larger disk, larger memory, and a bit of computation resources. Now, in spite of this, of being beautifully constant time in complexity, hash indices are not ideal for everything. They are not ideal for everything. The first problem is that hash indices do not support when range queries. Does anybody know what a range query is? Yes?
You select a range of centuries.
That is correct. Yeah. So instead of an equality, so the query we had here was an equality where century equals 19. So with an equality, you just put whatever is on the right side, put it in a smoothie machine and get the hash, right? What if you don't have an equality? What if it says century is lower than this and greater than this, right? It's in an interval. Then what do? You cannot just put these two values in the smoothie, right? Because that doesn't work. Because since it's a smoothie machine, I might have the beginning of my interval, let's say here, and the end of my interval here, but the rest could be everywhere because it's a smoothie machine. It just puts all the values all over the place. So there is no way you can handle range queries. You can only handle the equalities like this, which is called a point query, but you cannot handle ranges efficiently. Who sees that? Right? So we can't use the smoothie machine for that. Another thing is that the hash functions are not perfect. What's actually going to happen in some cases, here it was a simple case where it was behaving because all of these values nicely landed in different cells. The problem is that in real life, when you start having a lot of values, the smoothie machine is going to give you the same thing for different inputs. And then you're going to have two values that end in the same cell. It's no big deal. We can deal with that. We just make them roommates, right? We just put the two of them in here. But it's just that it costs extra when you look it up, because when you arrive here, you notice, oh, there's two of them. So you need to additionally figure out which one of the two it is. Right? Is everybody with me on that? Right? So that is the second problem. And the last problem is that if you want to avoid that, to have too many roommates, if you would like most of your values to be on their own, then you need a super large tables. You need maybe even more positions, an even larger red table, even more spots. And that, of course, is expensive, right? It's like the price of a rent in Zurich. If you want to have a huge table for your index, that's very expensive. So this is why hash indices have their limits. Yes? It's a smoothie machine. You can put whatever you want. You can put strings, you can put dates, you can put objects, you can put tables, you can put a PDF, you can put absolutely anything. It's magic. It's really a smoothie machine, takes anything, gives you an integer, right? And typically what happens is that when you program in Java or in languages like that, when you have a class, you can specify the hash function. And yourself, you can basically say, this is my hash function, and you're telling exactly how it's computing for the object. But really, think of a hash function as capable of hashing absolutely anything. Absolutely anything. Yes? Ah, the reason, so it would work in the case, for example, that you know in advance the interval of centuries, you know it's well distributed and so on, right? In real life, the problem is that you will have let's say you have doubles, you have decimal numbers, you have prices, you have that kind of stuff. You can't do this reliably, right? You could only do something like this if you, for example, you have a column that has a value that is guaranteed to be between 1 and 1,000. Then you could, of course, say, okay, then I'm taking a hash table with 1 to 1,000, so 1,000 positions, and then H is the identity, and I directly put them there, right? So you could do that, but the use case for this is very limited. In the real life, when people use databases, they really want to index everything. They want to index dates, they want to index prices, so you need something that gets an integer out of it, right? So it's like what happens if you put a smoothie in a smoothie machine. Well, you wouldn't use a smoothie machine in the first place, right? But the whole point of a smoothie machine is that it transforms fruits into smoothies, right? So the idea here is that you can transform anything into an integer, absolutely any type of value. Does it make sense? Yeah? All right.
There was a person also on Zoom asking about the second limitation.
Second one?
The second one, I think that was the collisions.
Because did it ring? It actually did. It didn't ring. Yeah. And it's too passé. I should give you the break. Normally it rings. I was actually waiting for the ring, but it didn't ring. Can you remind me of starting with this after the break? Yeah, but you deserve your break. So I see you at 17 past 11.